Hello, today's lecture is a continuation of the previous video recorded lectures that you can access on YouTube. Those lectures are intended as an introduction, the first one, and the second one is for core log integration for clastic sedimentary sequences. Today's lecture is about core log integration of carbonate sedimentary rocks, and we're going to talk about specifically the Sacroc field. And the Sacroc field includes several formations. We're going to talk about the Wolfcamp shale, and we're also going to talk about the Cisco and Canyon carbonate formations. Please verify the previous videos, understand them, look at the introduction, at the objectives, and I hope that this lecture is of your liking. Thank you, and all the best. Hello again. As an introduction to the lecture today, let me just say a few important things, give you a few important remarks about carbonate sedimentary sequences with special emphasis on storage and flow properties and responses of well logs across carbonate sedimentary sequences. As we saw in the lectures devoted to carbonates, there's a great deal of cyclicity in their genesis, and the process of diagenesis causes great variability in the pore structure of these carbonates because of differential dissolution and also recrystallization, opening of pores and fractures, and a number of other things that are intimately related to the initial sedimentation cycles and the differential dissolution because of presence of organic debris, relics, fossils, and all of those things that dissolve in a differential way, and then the action of the fluids interacts with the solid component of the rocks, causing even more differential dissolution and recrystallization. The genesis of carbonates is intimately related to open marine environments, precipitation, and depending on the location of the marine environment in reference to the sea level, it's very important for the genesis and subsequent modification of the carbonates. So there are many possibilities for these carbonate formation to take place depending on how far from land they are and how deep the ocean is at the place of formation. So because of that, there's great diversity. We are going to look at the Sacroc field, which has to do with a platform margin reef that was of Permian age. Now, the diagenesis of carbonates is a process that goes through geological time, and it has to do with the deposition itself, the compaction, the fracturing, the cementation, the leaching, the recrystallization. All of these things are going to affect the porosity and permeability, including the development of microporosity and variable pore size distribution in the carbonates. For instance, it's not very uncommon to see carbonates. This is a thin section that has even trimodal pore size distribution because of the original deposition, the interparticle porosity plus the cementation plus the presence of differential dissolution because of the presence of organic material that dissolve at a differential rate. All of those things are going to impact the pore structure of these carbonates. And also we have, as a consequence of the presence of fluids moving through this pore space, we are also going to have presence of recrystallization on the surface of the pores. And this recrystallization can come in a number of ways: dolomitic, aragonite, calcite, and because of this recrystallization, we are going to have different roughness along the pore structure. Consequently, when we look at core, this is a cylinder, a typical cylinder of whole core, we are going to see an excessive degree of pore variability. We can have fractures, we can have also opening along the fractures with recrystallization, we can have primary porosity, we can have vugs like shown here, secondary porosity, and as is a very wide distribution of pore and throat sizes that is going to impact the ability of these rocks to transport fluids across them. And the great variability is also affected by tectonic deformation, presence of fractures. All of these things are very common to carbonates where, once again, the genesis and diagenesis are extremely variable, and they can come in a number of ways. And it's very important when we do core log integration to look at cores, because visually we can not only look at thin sections that describe to us the degree of diagenesis, the pore structure, but also they can give us a very strong indication of the variability of pore and throat sizes, because they're going to have multimodal transport of fluid across them. The carbonate sequence that we're going to talk about today is in the Permian Basin, is located in the Sacrarok field that is currently operated by Kinder Morgan, and the Sacrarok field is a platform reef that is also bordered by the Cogdal field north of it. It's a promontory, as you can see here, with respect to the surrounding formations. A cross-section of these shows this promontory, this upper reef, and we have a number of wells penetrated through this formation. We're going to look at one of them. The hydrocarbons that are present in this formation have been produced for a very long period of time. Currently, as I said before, in the Sacrarok field, Kinder Morgan is the operator, and some of their enhanced recovery techniques are based on the injection of CO2, which is typically denoted or referred to as CO2 flooding. Here is another cross-section of the Sacrarok field. The location of the Sacrarok field is in the center, is precisely coincident with this promontory. In the upper part, we have the Wolfcamp shale. We're going to see rocks of that shale, Wolfcamp shale, organic shale, and then the wells that are drilled here are on top of this promontory, and they go through first of all, the Cisco limestone. We're going to see the boundary, and then below the Cisco limestone, we have the Canyon limestone, and all of these is saturated with oil. Before that, there's a transition zone, a capillary transition zone, that below which we have the aquifer. That's the stratigraphic description of this. So please pay attention to this, because we're going to be looking at rocks, as I said before, that go all the way from the Wolfcamp shale down into the Canyon limestone. And we'll see all the variability that we can expect in carbonate rocks across this very, very interesting stratigraphic feature. And just to reiterate on the stratigraphic column, let me show you here. We have in the Permian Basin, we have all of the phases of the or segments of the Wolfcamp A, B, C, and then Klein and Wolfcamp C is in this area. Then below that we have the Klein, and then the Cisco and the Canyon formation. The Cisco and Canyon limestones are all Pennsylvanian H, and the Wolfcamp is Permian H, where we're going to see those boundary. That's a very important reference so that we understand the relationship that these formations have. Over in a different place of the U.S. Fort Worth Basin, it's just showing this diagram to indicate how these formations relate. Here's again the Wolfcamp shale, and then we have the Cisco limestone, and then the Canyon limestone. We are going to see them in the core analysis. Here is a picture of the well logs. The pennies for size. We have the pizza boxes. We have the 3-inch hole core that was slabbed. We have 1, 2, 3, 4, 5 per box, and we have approximately 3 feet. So those are going to be the depth of the core. The well logs that have been given to you have already been depth matched with the core, so no worries about depth matching. We have a number of core plugs that were done here. Some of these sections will appear a little bit darker because some of them were already pre-washed and pre-treated, pre-clean. So some of these colors are not the original colors. We will see that. And the variability in this example is we're in the Cisco limestone here, where we can see great variability in pore sizes and presence or not presence of porosity and permeability. This just as an example. And there are also thin sections that come associated with this acrylic field. We have a great deal of diagenesis manifested here by the presence of dolostones and also by presence of Aragonite, Dolomite, all of these minerals that definitely come as a consequence of diagenesis of the original carbonate sediments. And here is a plot of one of the wells across this Sacred field in the Permian Basin. Is not the well that we have, but it's a very fair and clear representation of the things that we're going to see. That's the gamma ray log, relatively low values of gamma ray log. If you look at the spectral gamma ray log, you are going to see that there are sections of this column that have manifestation of uranium in the form of organic material, whereas the thorium and potassium components, they are extremely negligible. On the other hand, if you look at the resistivity logs, here are lateral log, deep lateral log, shallow lateral log, and super shallow lateral log MSFL. We are going to see variability, which indicates presence of invasion, but also we see a high degree of cyclicity, where the cyclicity is intimately related to the presence of low values of porosity. So all of these peaks in the electrical resistivity logs that you see here, the deep sensing electrical resistivity logs, all of them are associated with very low values of porosity and low values of permeability. The column that you see here is all plug permeability. We have hundreds of points or plugs that were processed in the laboratory, and what we see is an extreme degree of correlation between the local maximum of the resistivity log with the local minima of permeability. Please recall that the permeability values of plugs are here represented in a logarithmic scale. The values go from 10 to the minus 2 to 1,000 millidarcies. These cycles are very prominent because that's the way the deposition took place. And the effect, the presence of porosity, is due to differential diagenesis, as we're going to see from the core. Here we have the density and neutron logs expressed in limestone porosity units. They have a fair description of the porosity. In fact, if you plot these logs in limestone porosity units and you overlap the core values of porosity, you are going to see a tremendous amount of coincidence. They track 1 to 1. The density and neutron logs overlap, and they overlap with the core values of porosity, because that says that the dominant mineral composition here is limestone, so we have a great correlation. That is manifested here by all the plugs, an incredible number of plugs that were sent to the laboratory to measure core porosity. And here we have the sonic log. The sonic log is a very good indicator of rock porosity. Whenever you have fast rocks or short times of travel, that will be segments with low porosity, as we can see here. All of these peaks of the sonic log, those are all correlated with fast acoustic times, and those are due to segments that have relatively low porosity. The best porosity is always correlated with those sections of the wells for which the acoustic travel time is the slowest, as shown here. And those points also correlate extremely well with the presence of high streaks of high permeability. It's also very important to look at the photoelectric factor log that by and large indicates dominant presence of limestone, but we also have abnormal concentrations of certain types of minerals that are indicated here by these peaks. Those are also associated with these cycles of sedimentation and dominant mineral composition. And so despite the fact that the porosity is variable but not over a wide range, we have a significant variability in the permeability of these rocks. And we will see that as indicated in the core log visualization that we're going to carry out as part of this lecture. The actual logs that we're going to use for this analysis are shown here. Please, this is the SACRAC unit. The depths are given in feet. As I said before, the core and the logs have been properly matched. We have the gamma ray log, the caliper. We also have the deep resistivity log, the shallow resistivity log, and the super shallow resistivity log. We also have the density log in red, the neutron log in blue, and we have the photoelectric factor, then we have the sonic log, and then we have the spectral gamma ray logs separated here as uranium, magenta, and then we have thorium and yellow, and we have potassium in black, and then we have the core permeability. As we go down in this sequence, we are going to encounter the segments where we begin to have the core blocks. The upper part of this well is a Wolfcamp shale. That's what we see here. And then suddenly, right here, at this particular depth, we have a sudden decrease of the gamma ray log. That's where we enter the Cisco limestone, where the gamma ray log has negligible values. And then we begin to see these beautiful cycles in the resistivity logs associated with porosity values. So high resistivity, relatively low porosity, and relatively low permeability. That's what we see here. And again, we have the same description. What I did here is I pasted the logs as though they were in sequence. I cut them. In fact, you have the original PDF file, so you can lay this out directly. And what we're going to do is that we're going to match these logs at certain sections of the sequence of the core to relate, for instance, local minima or maxima of resistivity, or local minima and maxima of core permeability or of neutron density with, or PEV, with specific sections along this very interesting well. And these are other segments. This is the shallower and deeper part, where we can also see these beautiful cycles of variability. The cyclicity of the carbonate formations are manifested by these cycles in the gamma ray log, in the resistivity logs, and the neutron density logs, and in the core permeability, as we see here. Please note that as soon as we leave the Wolfcamp shale, then the neutron and density logs expressed in limestone porosity units, they overlap extremely well in some of the sections. We even see a crossover indicating the presence of light fluid lighter than water as we go along. And then we have more of these features. We are going to be looking at these local maxima of gamma ray log to see what they indicate. We are going to essentially cover a few of the sections to relate well logs to core samples, visually what we see on the samples, and what the well logs are telling us in terms of resolution. So we will see all of these points where we have core. All of those would be locations of plugs that were cut into the slabbed core. So that's the description of the well logs that you have a PDF. We will go and look at the correlations with core samples. And the summary of this presentation is exactly the same summary that I had in the previous lecture. All of the properties, all of the conclusions apply to this lecture, including the depth matching of core logs. And I have a few review questions that are exactly the same as in the previous presentation. I'm just letting them here for consistency. And I want, in closing, again, I want to thank Charlie Cairns. He will be a main presenter of this video lecture. You will see him in a minute. I'm going to introduce him. Then in the next video lecture, we're going to have Toti Larsen to explain us the core along the Eagle Ford. I also want to thank my colleague Jerry Lucia for giving us access to some of his figures, data, samples. And of course, I want to thank the Bureau of Economic Geology and the Hildebrand Department of Petroleum and Geosystems Engineering for their support of this core log integration activity. Thank you, and now let's move to the core viewing facility. And now we're going to look at this other piece of core, which is a carbonate. Here we're at the top, which is a pressure seal orchestrated by this shale. And then here we come, shale is here, it's very fissile, very anisotropic. And then we come here, and boom, we have a discontinuity between a shale and a carbonate sequence, and you can imagine what this will do to the gamma ray log. And then we come here, and that's a carbonate rock, and we move into the carbonate world. This is a sack rock, and we see lots of variability here, relatively high porosity and high permeability. Patchy, they're very patchy, look at that. And then we come here and continue to go over this section. I'm walking fast so that you see the incredible variability that we have in this well. Fractures, we have bugs, we have more fractures, we have also relics of fossils, more fractures, more bugs, high porosity, high permeability. In fact, you can see where oil was once present here, and we continue to go here. These we have the logs for all of these sections. Sometimes the presence of fractures is so prominent that the core breaks apart, and then we have more fragments here, and extremely patchy. Look at this, very patchy, extremely variable. Porosity is not does not have a unimodal distribution, is bimodal, trimodal, lots of microporosity. Moving along, you can see that there are in these cycles, some cycles have good porosity, good permeability, but then the cycles become very impermeable, like in this section over here. And we have different cycles that had good porosity, good permeability, good connectivity. The company that owns this well is doing CO2 flooding because of the variable porosity permeability in these carbonate formations, and also because of the presence of relatively heavy oil. And when we continue to analyze this, we have more variability. Please pay attention to the sections that look dark brown. Those are the good sections, but here we have another section where permeability is extremely low. The rock is extremely variable, you can see that here, but porosity is low and permeability is low. And then here we have a band of shale. Look at that. How did this one come into play? Who knows, but I'm just documenting the variability here. Good porosity, this section here has good porosity and good permeability, followed by a section that has no porosity, good porosity, good permeability. We continue to look at this, and then we see rocks that are very tight, and we continue to analyze this and see more variability. The rock becomes more brittle here, and sections that are even more variable as we come along here, and we continue to see patcher sections with good porosity, good permeability, and fractures, bogs, extremely variable rock here in Sackrock. Then we come to this other section and we see more variability, very tight rocks, extremely tight rocks, and will make beautiful mosaics for the kitchen, but they're not financially viable until we hit this part. And I want to show you, here we have a very thin layer of shale interspersed in this carbonate section, and then we have a section that has good porosity, good permeability. More to say about the variability of this rock. And then we continue to move along here. More variability. We see this. It's incredible how much variability we have in these carbonate rocks. Marks, we have stylolites, other marks of diagenesis. We have different fabric of the rocks. We have segments that are extremely tight, like this one here. Again, this would make beautiful mosaics for your kitchen floor. And here we have more stylolites. And then we move to this other side of the core over here, and we see the top of this formation, which is extremely tight. Please understand how these properties will give rise to variability in storage and permeability, to understand not only connectivity but variability in space. And here we have another section which has shale interspersed into this dominantly carbonate rock, and we see more of that. Very intense piece of rock. Here we have one of the first most beautiful examples of the discontinuity in rock properties that gets mapped into a discontinuity of well logs. We can see across here how we transition from a pure shale, fissile shale, an isotropic shale, to and because of this transition, the gamma ray log, which is here, transitions from relatively high API values. Let me show you the scale here. That's the gamma ray log. Transitions to very relatively high values to almost negligible values of gamma ray log. If you look at the spectral gamma ray logs here, all three logs decrease at the same time. And what else do we see here? Well, resistivity logs decrease. Sonic log is here. We also see that the sonic log indicates that the rock is faster here in the new rock compared to what it was in the shale. That's what we see here. Please look at the scale. There's the sonic log. That's the slowness, microseconds per foot. We were also looking at the neutron density logs expressed in limestone porosity units. This is minus 15% to 45%. So we have 60 porosity units across. And then we have the resistivity logs, the deep resistivity log, the shallow and the super shallow resistivity log. And this is the standard gamma ray log, going API values of 0 to 150. As I said, the typical way of sampling these well logs is one sample every half a foot when the tool is moving at about 3,600 feet per hour. That's a very common typical logging speed. The spectral gamma ray logs is the uranium is the proper one, and then we have potassium and thorium, potassium in black, thorium in yellow. So we're moving down here. And then this is where we see the drastic change on the boundary. right here. It's an important point, and porosities begin to be sampled along this segment of the rock. Here's an interesting section of the rock. If you look at the well logs over here, this is the resistivity log, gamma ray log. And so what we see on the resistivity logs is that we have a spike of resistivity right here, then we have a decrease, and another increase, another decrease, and another increase. If you look at the porosity data, that's because of the fact that in this section right here we have relatively low values of porosity, then the porosity increases, porosity decreases again, porosity increases and then decreases again. Those cycles are manifested because of Archie's equation into the resistivity logs. And I'm going to show you what those cycles are and what resolution we have. So the first cycle where we have very low values of resistivity is right here. This rock is very tight, very tight, continues to be tight, and somehow over here suddenly we begin to develop porosity. That's the section over here. That's where the electrical resistivity decreases. We are now over here. Before, where the resistivity was high, the rock was very tight, we saw that. Now we jumped into this cycle that has very low values of resistivity because of high porosity. And so we keep on being on that cycle right here. That's a cycle over here. And then suddenly we enter another cycle right here of very low porosity, and that cycle begins right here. So you can see why the rock becomes again very tight, as indicated by the log, the resistivity and the porosity logs, and then it becomes very tight, and this cycle ends right here. So that's another very tight rock, and then suddenly it becomes not so tight because the porosity increases. Look at, in all of these sections, please note that the gamma ray log remains about the same, so constant. However, the cycles of these rock indicate variability in the porosity and permeability. And also I want to mention that it is precisely in those places where the porosity is very low that we see very low values of permeability, and places where the porosity is high, in this example where the resistivity is low, it correlates very well with the high values of permeability. So we have this cyclicity on permeability as well. And that's what's going on here, that suddenly we come here and the rock of very low porosity, and suddenly we jumped into the rock with relatively higher porosity. It's a very good segment of the rock that has good porosity and good permeability. Looking at the logs again at 6780, we see that there are two cycles here that have very high values of resistivity because low values of porosity, very low values of permeability. And then the resistivity decreases because porosity increases and also permeability increases. So why it's happening that? So it turns out that this is the section of the rock. This is the upper cycle. The rock looks very tight, very tight. It has some chert inclusions. I'm talking about this cycle right here. That's the one we're looking at. That's the way the rock looks like here. And then we continue to go down, and suddenly we find a better class of rock right here. And that's because we are now navigating, so to speak, in this interval right here, which is somewhat variable, but on average has better petrophysical properties. And then we navigate on that segment. Please look at what the log is telling us, 6800 right here. And so we're going to go now to the next cycle, which is 6820, where we have a sudden increase in resistivity, decrease of porosity. And where is that? Well, that segment is right here. And again, we see another cycle with rocks that are very tight, extremely tight, with inclusions of chert, as you can see here. This would be once again a beautiful mosaic for your kitchen floor. Very, very tight rocks. That's this cycle over here where the resistivities are extremely high, and then the permeabilities are almost negligible. And then now we need to get out of this cycle to get into better rocks, and that's precisely what happens here. That suddenly we get into better looking rocks with better porosity and better permeability, and that's what we're looking at now is this segment over here. So please understand how these log properties correlate extremely well with the rock properties that visually we're looking at in this section over here. Now we are on this interesting section of the rock right here where we have a spike on the photoelectric factor log. Values of gamma ray log are very low. Resistivities are relatively low, porosities are fairly constant, but obviously something is happening here, and this is what we identify as a culprit. So there's a feature here. We looked at this with Dr. Charlie Cairns, but this appears to be the culprit of this, so there must be some kind of heavy mineral associated with this particular structure that causes this relatively high value of photoelectric factor. I want to show you something also very, very interesting here, which is if you look at this piece of rock right here, which happens very close to 6900, right here we have a pure shell right here embedded within a carbonate rock above and below. And guess what happens? Here is what the gamma ray log looks like right here. So we encounter the shell and suddenly we have a local maximum of the gamma ray log. Of course, if you look at the gamma ray log itself, you're going to see that the distance between the inflection points is actually much larger than the size of this segment of shell, and that's because of course the log is rounding off the corners because of shoulder bed effects. But this is very interesting. Look at this. This is 6886, and this is what is called a 96. It coincides extremely well. Second thing, we showed that the resistivities, especially the shallow resistivity log, does respond to the pointy nature of these, or the presence of this shell. High values of resistivity is a very tight shell, very low porosities, and very low permeabilities. Very low permeabilities. So it's only this tiny segment over here that causes the presence of a local maximum of the gamma ray log. That's a beautiful correlation that serves to even depth match the logs that we see across here. Here is another very interesting segment of this well where we see a relatively local maximum of the gamma ray log, and that local maximum of the gamma ray log is originated by this shell segment over here. It is very close to 1 foot length of shell. It stops here, it doesn't go in the next section of core, and that's where we see this local maximum. And you can see that based on the distance that we have between inflection points, well, the log registers the presence of that with the local maximum, but probably the local maximum is subdued because of the relatively thin layer of shell that we have here. And then above and below the gamma ray log is constant. That's what we see here, above and below. But look at that, just slightly above it, we have a very tight rock. That's what we see because of the increase of resistivity log, and that's exactly what happens with this rock. It's very tight. It's a very tight rock. It has a lot of fossils visible to the naked eye, where it's very tight. And that's a section that anticipates the shell. And that's exactly what we see in the log, that the shell is here, and preceding that section we have a very tight section. And then as you go below that, then the resistivity logs decrease because the porosity increases, and that's exactly what we visually see on this rock, that suddenly the rock begins to have better properties, better porosity, and also better permeability. And as we go down in this section, in the log, we see that eventually the rock becomes tight again, very low values of porosity, and that happens in somewhere about here. That's where the rock becomes again tight, very tight, again a piece of rock that you can use for your mosaics on the kitchen floor. Very interesting. So we have a great correlation here between the well logs and the visual properties of the rock. And here we are again at the Bureau of Economic Geology, famous center of geological studies around the world. And with us we have an excellent, very well-known scientist, Charlie Cairns. He's the head of the Department of Geological Sciences of the Jackson School of Geosciences. And today he's a super busy person, so I'm very happy that he's here with us, because anybody who knows about carbonates knows the name of Charlie Cairns, alongside many other luminaries here at the Bureau, right? And Charlie also heads a consortium on carbonate research.
Reservoir Characterization Research Lab.
Excellent. Thank you so much, Charlie, for being with us here. I appreciate your knowledge. Here we have this beautiful sack rock core from the sack rock field in the Permian Basin. And Charlie actually gave us all the logs here. So we have absolutely all the logs, gamma ray log, resistivity log, nuclear logs, neutron density, PEF, and we also have spectral gamma ray logs. So we're going to walk through this beautiful example of carbonates with Charlie, and we're going to ask him a few questions to understand the nexus, the relationship between well logs and core data. So Charlie, the upper part that we see here, should I say the upper part, or yes, this is the upper part, right? Yep. So let's start from the upper part. Yesterday we started from the lower part, but this shale is serving as a pressure seal for the reservoir, right?
That's correct, yep, the Wolfcampian deep water shales.
Excellent, and you can see that because it has very high values of gamma ray, as we see here, and then suddenly we have a drop in the values of gamma ray, and that happens over here. That's where we have the boundary, right there. Let me move the logs. That's where we have this boundary. The gamma ray log begins to decrease here because of going from a shale to a, you told me this is a turbidite segment, right?
Right, yeah.
And then
carbonate turbidite.
And then we go to the pure carbonate sequence. So how old are these rocks, Charlie?
So they're around 350 million years old. This is the uppermost part of the Pennsylvanian, otherwise known in Europe as the Carboniferous.
And then if you worked we did this exercise with Toti Larson. If you were to say this is, we have 2 feet here, how many thousands of years of history of the Earth do you have in 2 feet here?
Based on our understanding of very similar modern carbonates, probably a meter of rock here is probably worth around 5,000 or 6,000 years of sedimentation.
5,000 or 6,000. You know, it's very interesting because for the Eagle Ford, that was about 40,000 years.
So the trick here is that we have periods when the carbonates are very active and they accumulate pretty rapidly, and then the glaciers start to grow again. Sea level goes down by 100 meters,
yes,
and the carbonate platform is exposed and nothing goes on. So for every 100,000 year cycle, you have maybe 5 to 10,000 years of deposition and 90,000 years of missing time, erosion on the,
on the platform. So it's not a continuous process.
Accumulation, yeah, so if we average it, we could say, well, that's a meter of rock in 100,000 years, but that's time average with 90,000 years of unconformity and 10,000 years of deposition.
Yeah, this is just to give the students an idea that the reason why rocks are so variable is because we're looking at a very long period of time when we see them.
Yep.
And that's not obvious to us because we live in a very short span, and we try to reflect our common life activities with what happens in geology, and that's not the case usually. So it's important to bring everybody to that context. So as we move along here, the carbonate is changing properties. We expect that the gamma ray log, the resistivity logs, the neutron density logs, sonic logs, everything will change across here, right? But from my note from the SACROC is that the gamma ray log tends to be very low,
Right.
except at certain places. And we do have variations of porosity, but most of the time the porosity is about 10%, 5% to 10%.
Yes, and until we get down to the canyon part that has the significant variation from 5% porosity, which in a limestone is pretty tight,
Yes.
less than a millidarcy, up to 10 to 15%, where we're getting 10 to 30 whatever millidarcies, decent permeability.
Yeah,
But up
and-
here, that's usually the old people used to say, or the original sort of Permian Basin people, when they would see a big, thick, clean gamma ray interval, they would call it, that's the reef. You know,
Oh, okay.
that would be the nomenclature. Now it might be a carbonate sand. This is all carbonate sand. There's no reef here, but because it had a clean gamma ray, pretty high porosity, that got the nomenclature of the. So this is the horseshoe atoll, or the reef is what people refer
Yes.
to it as.
Now, the owner of this core is Kinder Morgan, right?
Kinder Morgan,
And
yeah.
they're doing CO2 flooding.
Yep.
Okay, so that's a very important thing because CO2 flooding is done under certain conditions of porosity, permeability, and fluid properties. So we'll talk more about that. So then we go from here, we move to this other section, right?
Right. So this is pretty uniform until I think when we hit down here in the 6400 range. Now we're into a completely different setup. You know, it may still have similar. Well, I think the porosity is lower here than it was up just a bit higher. But this is the reef environment proper. So we have crinoid columnals from the standing sea lilies, and then there's lots of these dark potato chip-like features, which are a type of calcareous algae that build reefs in the Pennsylvanian.
Many of these features are hardly observable from well logs, by the way, but my intuition tells me that some of these features that you're pointing, such as those fractures, that those perhaps have a very important influence on the fluid transport properties, right?
Yes. I mean, the only thing you might be able to do with logs would be work an image log in here. The image logs might help you see the patchy nature of the reef versus the rather uniform nature of the carbonate sands.
Yes. Yeah, so that's important to know for all the students who use well logging to anticipate properties from carbonates. They are into a very tough problem.
Yes, Lucia used to say there's no relationship between porosity and permeability in carbonate rocks, and all the students would get very upset, and then he'd say, well, it's only a relationship between interparticle pore space and permeability.
I just want to say that Charlie had the pleasure and honor to work with Jerry Lucia, right? When Jerry comes
Quite
here.
a few years, yeah.
And probably also with Robert Falk.
Oh, yeah. Oh,
Correct?
absolutely, yeah. Yeah.
I mean, these are just heroes of carbonate petrophysics and geology. It's very, very. Lots of people have worked at the Bureau of Economic Geology on carbonates, and I should say this. Maybe people are going to get upset at me, but I think the Bureau has the leadership on carbonate research.
Carbonate research and reservoir studies, I think we're right up there with pretty much any of the major oil companies. You know, we have as
Yes.
good a group as anybody. So.
That's what I know. So this is one of the sanctuaries of carbonate geology. So as we move down here, we also see bugs.
Yeah.
And that's important. You know, I talk to my students about the fact that when you look at carbonates, as opposed to clastics, in clastics you have one modality of pore size and throat size. But in carbonates you can have situations when you have microporosity, mesoporosity, macroporosity, touching bugs, non-touching bugs, all kinds. And so it gets very complex to predict permeability or flow.
Absolutely, yeah. Be hard to use. I mean, there's always tricks that you can use with the sonic log versus the neutron density, and you guys know all those tricks. But it's really important to have if you're going to do a modern study of carbonate reservoirs, you pretty much have to come out and look at the rocks.
Did you hear that? You have to come and look at rocks. This cannot be done on the computer, not even with artificial intelligence.
Not yet.
Not yet. Okay, that's good.
Eventually, that'll replace us.
Yeah.
Yeah.
And then we're looking at, but certainly what I see from here, Charlie, is that these rocks tend to be very patchy, and patchy is a term that we tend to use in petrophysics to indicate that the variability of the petrophysical properties, the connectivity, the storage of the rock is extremely variable, right?
So we have done multiple studies on these rocks where we used a mini air permeameter and tried to map permeability at the centimeter scale versus the whole core scale versus the plug scale. And we find that it's common in carbonate rocks like this to have 3 orders, sometimes 4 orders of variability in 1 foot per section. So I mean, it's so important to understand the scales of variability.
And what about the connectivity between wells?
So here and in fields just to the north, there are places where we have cross well tests that have breakthrough in a half a day. You know?
Yes.
So they're very complicated and very difficult. You know, of course, with CO2, that's very expensive. You don't want to have that kind of fingering and lack of sweep.
The recovery factor will be very low, right?
Yeah, and in today's world, when it's already a cost-cutting world, that's very difficult to deal with.
Yes. So it's important to understand the variability. When you look at well logs, of course, you don't see this high degree of variability, and even if you use sometimes borehole images.
There's a nice view of some of the reef formers. That's the phyllioid algae there, those wavy potato chips. And then here's the bryozoans.
We have been looking at the photoelectric factor log, and this is what I see is that the photoelectric factor log right here increases significantly.
And then there's the structure of one of the bryozoans right there, the little fronds that would have been almost like modern sea fans.
Yeah, some of these features, forget about seeing them in logs.
No signal in the log. They just help us kind of read the history, you know. So Lucia would always say, well, you know, I don't care if it's a fluid grainstone or a crinoid grainstone, it's just a grainstone. And I'm like, yeah, that's for the petrophysicist maybe, but for the geologist, we're trying to unravel the history and we might learn something. So these are the things that I think you were seeing on the gamma ray log, Carlos.
Slightly high values of
slightly
gamma ray.
higher rate values of gamma ray in here versus the carbonates above and below. And these represent marine transgressions, which are common across the reservoir. And we commonly can map these with the gamma ray porosity couplet and have been able to correlate these flooding surfaces across most of the north platform of sac rock. And that gives us a vertical permeability structure to the reservoir. And then, of course, it's combined with all the complex fracturing, etc. But these flooding surfaces, and you can see them across the way in that next table, the tan versus gray, those are mappable units through 500 or 600 wells. I can correlate those. So that gives us the lower part of the reservoir is very strongly vertically stratified. And then the upper part is mostly the big massive reefs.
I tell my students that one common way to study carbonates is by their cyclicities, right?
Yes, that's the cycles that we use.
Exactly, and those cycles are also mappable sometimes on well logs, by the way.
Oh yes, absolutely.
Yes.
That's how we put the framework together for this reservoir.
And have you looked at magnetic resonance for measurements for the carbonates?
Not here
Okay.
that I'm aware of. You know, they may have since I was working on this field, but you know, the magnetic resonance studies here, I'm not aware of.
Okay, so we do some of those in Petroleum and Geosystems.
So they're giving you things like pore size distribution
exactly,
and stuff.
yes.
Yeah, we had the one student that was working on that with me for the Thamama reservoirs in Abu Dhabi.
In Abu Dhabi, yes.
Yeah. Yeah, here's another one of these flooding surfaces here with the basal conglomerate associated with big crinoid columnals. So you would add a very grainy porous rock below, high energy shallow water. That's deeper water with the shales, and then back into the shallow water, high energy porous stuff.
Yeah, that's one of the things that I was going to ask you. These are shallow shelf, right? Deposits.
Yeah,
Most-
we're up on an isolated atoll, and the top was probably in anywhere from a half meter to 20 or 30 meters of water depth.
Oh, excellent. And then oil got here from what formation?
Most likely it's coming up into this system through the Pennsylvania. There's some pretty rich source beds in the Atoka, and then also down in some of the lower Pennsylvania, maybe Barnett, possibly,
Oh, okay.
and then occasionally Woodford. I don't know if any, in the Permian Basin, our problem with geochemistry has been that the oil's here, so why do we care? I'm not going to do a big source study because all my structures are filled. I'm not worrying about migration, pathways. If I drill a decent structure, it's going to have oil in it, so don't bother me. So it's been.
But it's interesting from the viewpoint that the migration itself tends to favor the areas that are better connected. So if the rock has good porosity, good permeability, those are the ones that are going to be migrated quicker, right? But if you have enough geological time, probably everything becomes charged eventually, right?
This is the whole game, right? I mean, and plus, there still was so much more hydrocarbon that never migrated, which is the whole unconventional game that people are drilling now.
Yes. So
But
here,
the conventionals, this is still where the big oil was. I mean, this Horseshoe Atoll had 4.5 billion barrels of
Wow.
oil. It's a world class. It's not the Guar field, but it's a world class.
yes.
So now you can see the
And-
cyclicity really beautifully. So there's a grainstone here, and then there's probably a karst breccia with all these fragments. So that was when the glaciers started to grow. The shelf got exposed, weathered to freshwater diagenesis, and then here the glaciers melt, sea level comes back up, and you get this nice dark, slightly hot on the gamma ray flooding surface, and then you pick up a subtidal reef, and then it goes into grainstone, and then the next mudstone over there, and then when you look down the table, you can see our tan, oil-saturated, grain-rich facies, and then the next flooding surface just down the way. So these cycles are very well developed.
And there,
in
I have
this
to ask you
field.
this question. I know for you it's super simple, but for my students, these cycles are also associated with so-called Milankovitch cycles,
This
right?
is, we think, kind of a pretty good representation of a 400 kiloyear long-term eccentricity cycle in the
Okay.
Milankovitch band.
That's
That's
good.
about the right periodicity.
That's the kind that is. It's important to remember that the clock here is running very, very slowly.
Yes.
So that when you look at this, this is no way the active light that we have today, where everything happens so fast.
Yeah, a major hurricane come through an area, and it might deposit that much rock. So
That might be, see?
like
One
maybe
event.
1 or 2 centimeters. That's it. It's not going to be a hurricane's not going to generate this whole succession.
Exactly.
This is thousands and thousands of years.
Unlike a classic sedimentary sequence where you can have very thick developments, right?
Yes. Here, of course, the carbonates, as they grow, they get cemented, so they tend to, once they get situated in place, they tend to stay there.
So on the cementation, now that you talked about that, these rocks are cemented in multiple ways, right?
Right. Yeah.
Do you have Aragonite, Dolomite?
So here, the typical modern carbonate starts out with 70% porosity, and that's always an interesting thing. How do you go from 70% to 10%? What are you doing? And this reservoir is kind of unique in that we have at least, maybe 30% of the porosity is lost to early calcite crystal precipitation. But the fact is then the remaining pretty high, 15-20% porosity is still here. If this rock was not isolated and buried by the Wolfcamp Shale, this would be a tombstone. We have outcrops of this in the Sacramento Mountains and other places, and it's an absolute tombstone. But this reef was buried by deep water shales, and that protected it from later groundwater related cementation. So usually the limestones, if we see the Edwards or something out here, it just continues to pick up calcite cement through time, and it shuts it down to a few percent porosity. But here, because the reef drowned and then the deep water shales covered it, that kind of protected it from a lot more rainwater-related cementation and preserved it as a nice reservoir. I guess it's almost world-class.
And by the way, Charlie, what is the recovery factor of these carbonates, more or less?
Still on the, well, with the CO2, it's over 50%.
50%, wow.
Yeah, with the CO2 sweep, it's very good. Water flood, it's pretty heterogeneous. It was lower than 30.
Yes, that's important. And that's bad because there's a lot of oil in place that will never make it out to your cars.
Yeah, we're going to have a lot of cycling. There's a lot of moldic porosity too, right? Because
Yes.
these icehouse reservoir, we call this an icehouse reservoir because it has very strong Milankovitch cycles. So it was during a time in Earth history called the late Pennsylvanian Ice Age, late Pennsylvanian, early Permian. And so all the ooids in here and stuff were all aragonite. And then the freshwater cement that came after the glaciers caused the sea level to go down, that leached all the ooids. So you got a lot of oomoldic porosity, which gives the petrophysicists headaches because you see 25% porosity and 2 millidarcies permeability, and you're wondering what went wrong with your reservoir,
I call that fun, not headache. And then, but some of these sections, if I remember the logs, porosity seems to be very high here.
Yes.
In fact, this section right here, if I look at the well logs, it indicates very good permeability.
Looks
So
like good perm to me there.
Yes.
Yeah. And then boom.
Exactly, that's
This
very
is one of our
tight.
cycle based. So when I built the reservoir model for this, I would map for every one of these cycles. I have 3 surfaces. I have the base of this tight flooding surface, the top of the tight flooding surface, and then the top of the cycle. Because if I give it to my geostatisticians, no
pun intended. I don't do geostatistics.
If I gave this to Larry with that surface and this surface, my flooding surface would disappear stochastically. But if I give him that surface, and then that surface, then it goes into the model and stays. I have 2 layers. I've got a low permeability layer and a high permeability layer. Even with the facies proportion curves, I can't preserve this segmentation in these kind of thin cycles without deterministically putting in a well-logged top, here, and there.
Yeah, actually what you say is very important because in fluid flow in porous media in reservoirs, the presence of baffles or seals is probably much more important than the presence of high permeability streaks. So the effect that seals and baffles have on the connectivity between wells is sometimes much more important than the presence of high permeability streaks, or even as important.
It's at least as important. And,
Yes.
And we had, because these flooding surfaces have this nice clay-rich intervals in here, they're easy to see on the gamma ray log and the porosity log for that matter. And that makes it very mappable. This is the clean gamma ray, high porosity, upper grainy part of the cycle. This is the high gamma ray, low porosity, lower part of the cycle where the transgression is occurring. And those are quite mappable on the wireline logs.
Yes, they are, because you see very high resistivities because they have low porosity. So that's actually what we often see, that in carbonates the resistivity log correlates extremely well with the porosity.
Right.
And then we come here and that's the end of the cycle. And by the way, if you look at the resistivity logs of this section, they indicate, and also the presence of invasion, the differences between shallow, medium, and deep resistivity logs. This section has very good porosity and good permeability.
You can actually see the stratification because it's a grainstone, so it would have been wave reworked, and it's been laid down by currents. So all the low angle layering in here has to do with ripples moving across the seafloor. So it's a very high energy setting that this was deposited in. This is definitely one of the more mappable cycles in the reservoirs. I remember.
And probably one of the most productive ones, right?
Yes.
And then here, Charlie, is this a shale?
Yeah, that's one of our shale zones there, and
So
we
how
were
did
talking about whether or not there's something missing from the core recovery. I'm a little bit nervous about that one.
But I just checked the gamma ray log here, does indicate a very high value.
Yeah, I suspect somewhere in the core handling process, somewhere on the core, on the rig floor, we're missing some of our shale, which is a bit of a nightmare because those are so important permeability-wise for the reservoir structure. That's why this core, because it was only taken, 15 years ago or 10 years ago?
Don't remember.
It's not that long ago, so and it pretty much came here. So this is in much better shape than some of the older cores in this field, which was, I think, developed in the mid-50s.
Oh, okay.
So some of the old cores just don't show the same
So
features.
it's also very important to think of everything you're saying, because at the very end we need to extrapolate this away from the well, right?
Yes.
And extrapolation needs to be done with geological conceptions in mind, not just statistical
Hopefully.
concepts, right?
Hopefully. We can hope, we can always hope.
Yes, well, that's the idea. And then here we have a more complex section.
Yes, this is like this all the way through the reservoir with all this chert. So these are all chert nodules here, areas
chert
of
nodules,
silica
okay.
replacement.
I have seen many of those in the Pedernales
Yes,
National
absolutely.
Park.
Yep. And I don't know why this one zone was. It must have been a diagenetic front of some sort, because many of the wells that core this deep, and we're starting to get down into the field, but many of the cores that drill down this deep have this zone of silicification in it. Of course that shuts down porosity at least locally in here. But this is still another beautiful high energy grain-rich zone. These are all fusillinids that are forming the grains here. So this is a beautiful carbonate sand again. Lucia type 1 grainstones. Yeah.
Yes.
And then these are your cycle-based muds here. The beautiful fine-grained mud. So that's going to be, less than 5%, 4%
Relatively
porosity.
high values of gamma ray here.
Yeah.
Sometimes. Well,
Yep, sometimes. And these stylites, when you see those stylolites, that's usually where you're starting to get the high clay insoluble residues, and that'll give a spike in the, because all the clean carbonate is so clean, 25 API.
Yes.
So this is not going to be a huge signal, but you'll find that the carbonate stratigraphers, we usually set our gamma ray curve from 0 to 50, whereas the sandstone people always carry 0 to 150 or something. So we always try and amp up the gamma ray signal so we can see these smaller anomalies.
I also see that the way this core is breaking up is different according to the different sections, right? That's important for mechanical properties of rocks. But do you see any correlation between geological properties, genesis, diagenesis, and the way the rock breaks?
In this one, we haven't done that study, but I would say in other very similar sections where Chris Zahm has gone through with the unconfined compressive strength, the Schmidt hammer, we have very nice ties between the mechanical properties, the sonic velocity, and the rock mechanical properties. And fracture distribution. So yeah, definitely, that's something we would see typically in here. That these lime mudstones and stuff, which are very tight, will tend to fracture more easily. And then the grainstones that have enough interparticle pore space, the fractures tend to diffuse, they break along grain boundaries, and they die out. Whereas in the muds, they typically propagate right through the
what
bed.
you're telling us is very important. That's what some people refer to as ductility and brittleness.
Right.
And that's actually very important, that it has a correlation with geological genesis and diagenesis. That's
Yes.
one of the important things.
Yeah, I think it plugs in pretty well.
Yes, and then we move to the other part. Is it over here? No, this is the end, right? No, we have.
This is the lower. So I think this continues on, but now we're into, instead of those ones that had a lot of ooids in them, these cycles, we still see the same flooding surface mudstones going into the grainier carbonates, but now in the lower canyon, almost all the grains are the big fusillinid forams, which we find also in the Permian. But the big white grains are a large benthic foram, and they sometimes can be completely dissolved out. But still we see the same cyclicity, right? We got grainstone or grain-rich rock here, low porosity permeability mudstone down below it, cherty again. So that,
And I see out some stylolites here.
Yep.
right here.
Yeah, stylized
They
here.
look like well
yeah.
logs, by the way, Charlie.
Yeah.
One begins
There's
to
a saying about that, you know. I think
one begins to see well logs everywhere, huh? Okay. and now
okay,
here,
Carlos, you know,
and this.
that's their chert nodules. Yeah.
Chert nodules,
yeah.
just similar to what we saw before.
Yeah, very similar. These are all, and I think here we do have in these subtidal muds, there used to be a lot of silica sponges. So probably what's happening here is that you have a local source of silica from the dissolution of the little monaxon sponge spicules that dissolve out relatively quickly and precipitate as nodular.
Yeah.
Features.
One of the things that I tell my students is that this geological knowledge is just not excess baggage, but it's very important for understanding properties. But you know, I have to tell you something, Charlie, that sometimes students get very anxious because they have to memorize a lot of different terms. But what I tell them is that's not the important thing about geology. The important thing are the processes.
Well, I think, you know, like the thing that's hard to get across to the students is that, you know, you could have two students out here and like I could come out and I've done whatever, 40 years of field work and worked a lot of different fields. And I look at a core like this and I start seeing what it means in terms of the three-dimensional aspects of the reservoir, you know, pretty quickly. Whereas, you know, when I was a student and I first started looking at this stuff, I started to wonder, what details do I need to record? You know, there's infinite detail here, you know, and you could just drown in the detail and never get the big picture. So it gets a lot easier with time because you get this, you know, I don't almost ever worry about the stylites, or, you know, there's certain things that I just filter out, you know, and I kind of work the larger scale framework. And then I always work in a team with a petrophysicist or somebody who can help and tease out the actual stuff that we can make money with the logs.
That's very important.
So, you know, between the team, you start to get a better understanding, and then the seismic data in this field was critical for understanding the three-dimensionality.
And also, it's very important to know the relationship between geological processes and the effect that they have on fluid flow properties, right?
Absolutely. You know, this is, you know, we had a crummy log suite. When Lucia and I started working this with the old Chevron data, it was, you would not have been happy. It was just gamma ray and a calibrated neutron porosity log, and that was it. And so we had to make up porosity permeability relationships. We had no logs to do it with. So I would tell them, you know, this zone is a type 2, or this is a type 3, and so we would just, based on the core, we had 16 cores and 600 wells, all these normalized gamma ray neutrons. And so we just basically made up the flow zones from the core data and the cyclicity, and then we had to kind of fit the transforms, and because all we had was total porosity. We didn't have anything else from, no resistivity curves, no sonic logs, no nothing. You know?
That's
so
pretty much.
It was, but reservoir characterization, we would always say, is, you know, is kind of like making the most out of whatever it is you have. You know, you can't start bitching about, well, I don't have this or I don't have that. You know, it's like, that's not the job. The job is describing the reservoir.
Yes.
And so you work with whatever data is that you have, you know, and yeah, you don't have modern, you know, not even PE logs, PE logs are not modern, but, you know, you got none of that.
No magnetic resonance, which are very expensive.
Yes, that's right, the NMR.
And then here we have a section that is also very tight. It looks very tight, and the porosity is very low, by the way, and the resistivities are very high here. But again, we have some patches like this one that seem to have very good porosity, very patchy.
This was not fun.
No.
For me, I didn't like describing this part.
There
Too much variability.
There are some fractures here, which might create conduits, but they're not very well connected over long distances.
The information we had in here, I think, was saying that there was still pretty good fluid flow in this zone, but, you know, we could never explain that with the petrophysical properties. So there must have been a connected fracture network, maybe in these cherts or something, but...
And that's actually important because you may have a well that penetrates to this rock, and unfortunately might penetrate it in not the best petrophysical section of the formation, right? And so it's very hard to extrapolate laterally away.
Yeah, I mean, all this silicification, it's a diagenetic overprint. It's usually not mappable. You know, whereas the cycles, which are the sea level controlled cycles, those we can map around
Oh,
the
okay.
reservoir. But these patterns here, you know, diagenesis is always just one more layer of complexity.
Yes.
I mean, the big picture is, I think, that from that mudstone here and all the way down to this one here, that's one of these depositional cycles. But all this mess, all this partially silicified fuselinated stuff in here, that's really, you know, that would be below the level I could map.
Yes.
You know, I would have a unit here, one here, and then one starting at that next dark mudstone, but I wouldn't be able to capture that variability there myself. I would just have to leave it alone.
And here we have another fragment of shale. Actually, I checked the gamma ray log, and this is the largest value of gamma ray log that we have here. So it's a shale.
Yeah.
So how did the shale get here?
How did that?
What happened here? I mean, this defies all geological knowledge, huh?
My guess is that we're looking at these limestones that were deposited during this time of peak glaciocene are so complicated. You know, it does not surprise me that we can't explain a foot of rock here and there, because I take people out in the outcrop now in the Pleistocene, which is the equivalent of this kind of thing, and you know, people don't see any of the stuff that I'm trying to show them. You know, they just completely, you miss it, and you can see 3 rocks sitting on top of each other, and they're each separated by 200,000 year unconformities, and nobody can tell that there's any time missing at all whatsoever. So this, having a complex thing like that, you know, and not being able to explain it, I'm like,
No, and also it's the fact is
I
that the clock is
expect that.
running so slowly here compared to what we are.
This
used to see.
could be a little shale drape, and then if we stepped back and saw the outcrop, there might be like a 30-foot high sinkhole, you know, and then these high karst towers, and then this was a little shale drape in the middle of it. You know, it could be that complicated.
Yes.
In 3 dimensions, but we're stuck with 3 inches of data. You know,
Yes,
that's all we have. And an imagination.
A friend of mine once told me that it would be very nice to have a log that could see 100 meters away from the well
Yeah.
with very high resolution.
Yeah. That
And
would
I
be
said,
very
good
nice.
luck, because that's against the principles of physics.
That would, well, you know, I think not. You know, if we talk to Sergei Fomel, you know, I mean, these guys are imaging below salt, you know.
Yes.
They're imaging a reservoir target below this huge salt canopy. Well, that's, you know, they're using all sorts of weird ray tracing and different things. I mean, admittedly, this would be like, you'd be trying to pull out all the data. They're just trying to get underneath the salt and see what's there. But it is amazing what can be unraveled out
Long
of these
distance.
physics. It's just
But the wavelength is very different. We will
Yeah.
not be able to see the features here.
no, you would see
So
something very
so we're
general.
walking again over a very tight section. Lots of stylolites. I see lots of stylolites here.
Yeah, so usually that means, at least one of my rules of thumb is in the cleaner limestones, you see the big tooth and socket stylites, and then in the ones that have more clay in them, you see the lower amplitude, what we refer to as horsetail stylites. So these features here. So I mean, that's a stylite, but so is that, because a stylite is just a pressure solution seam.
Yes.
And so the cleaner limestones will have the high amplitude tooth and socket features. The clay-rich ones will have these kind of wavy type of anastomosing, and because they show up because you have insoluble residues. You have silt and clay minerals accumulating, sometimes pyrite on those, and that's why they're so easy to see. But they're just areas of different solubility that are coming together.
Oh, okay, very interesting. Of course, none of this is observable on the well logs, by the way.
I mean, the image logs, sometimes you can pick up
They have to be
stylite
very
stuff.
thick.
Yeah.
And very interesting also from the mechanical point of view, because I can see that they're breaking in different ways.
Yeah, and sometimes fluid flow. There's some famous reservoirs in Canada and the Mississippian where you can see these halos, because this amount of stylite, right, that means there's that much rock missing. And so that calcium carbonate sometimes just dissolves and then reprecipitates locally. And so you can see zones, halos of cementation around the stylite. And so these things wind up being local permeability barriers in reservoirs.
Probably we're seeing some of those being formed now on the Edwards.
Well, I'm trying to think, in the in the big thermoma fields in Abu Dhabi,
Okay.
they would refer to these stylite zones as flow barriers.
Oh.
And it used to bother me that they are low permeability and all that, but the deal is that the zone where the stylites are forming is a zone of low depositional energy where a lot of clay accumulated, and those are where you get the solubility contrast, and that's where you get the swarms of stylites. And so it's actually not just a random pressure solution zone. The pressure solution features are following a depositional pattern, and that's important because then I can predict for you what the depositional pattern is going to do. Whereas if I just wave my hands off and say it's a pressure solution zone that's a flow barrier, then I don't know anything about it.
Yes.
So that argument always goes back
That's
and
good.
forth.
And now we go to almost the end of these beautiful.
Yep, still have our cycles, right? Really, here's
Yes.
the mud-rich base of one of these cycles going up into a beautiful grain-rich interval here, and then that's the top of that cycle is right there. You can see all the particles there, and then that's going into the mud. So that was the top of a cycle, comes down.
And by the way, those cycles cannot be seen with well logs because I don't see a physical.
Some of them
Well,
we
at
can't.
least that one.
Well,
Some probably
I'm willing to try. I think we should
Okay.
try. And then for sure, we could tell this from this stuff on logs. I'm willing to bet a case of beer on that one.
Okay, good. Maybe make it 2 cases. And then here we have another shell.
Yeah, that's a real banger there. No problem with that.
Yes.
And then right underneath the shale is another grainstone.
Yes.
So the cycles are typically asymmetrical. There's a flooding event, a rapid deepening, and then a gradual shallowing, and then a big sharp top, and a rapid deepening and a gradual shallowing again. So they have a asymmetrical upward shallowing cycles is what we call them. And this one's a little bit different, this last one, because it has another small patch reef here. So these are the phylloid, here's all the phylloid algae again.
Oh.
All those crinkly things are all the green calcareous algae. And then on top of that is a little grainstone shoal.
Of course, if you see all of these through the eyes of a thin section, you will see a lot.
It's spectacular.
Yes.
Very spectacular.
And that's what you guys do in addition to all of these, right?
Yeah.
You select places for thin sections.
All these spots here where you see cuts are where there's been a thin section taken here and over here.
There's a
Over
thin section
here.
spot, yes.
Yeah.
And those are very important because, once again, I always say that the invisible sometimes has the most important effect, right?
Well, and if we want to do pore typing, if you want to do anything now, of course, all this stuff that's starting to get pretty automated,
Yes. And here we come to the end. At least the end of the core.
No, into the core, I think we still, to get down through this is just touching into the Strawn. So we have Strawn, Canyon, and Cisco. This is the Strawn part of the reservoir, which is overall not as good quality.
It looks very terrible, by the way. It looks very tight.
Yeah, pretty tight.
I mean, I will make very nice mosaics for my kitchen from here.
Usually when you see something that looks like a good coffee table, it's not a good reservoir.
Exactly.
Usually there's an inverse relationship.
Well, thank you so much, Charlie. I wanted to thank you on behalf of all the students around the world, for sharing your tremendous knowledge. It's very kind of you to be with us. I very much appreciate it.
Pleasure to talk to you.
Thank you, and you will get a lot of likes and hits from YouTube.
Awesome.
Thank you.
Thank you.
And with that, we conclude part 3 of the core log integration. Many thanks to Charlie Cairns for being so nice and for sharing his superb knowledge and experience with us. Thank you, Charlie.